Uh, okay, the region. So the region is bounded by these two curves, as well as the region is inside the first quadrant. Okay, so that's the important information. Yeah. So to sketch the region, of course, you have to sketch y equals to 2 minus x squared. Okay, in this case, uh, this one, y equals to 2 minus x squared, and then here y equals to x squared. So the region will be, uh, since it's only on the first quadrant, so we only have this one. Okay. So this is the region. Okay. This one. Okay, so the green one. Okay. Okay. And then the question is, uh, the region is revolve about the y-axis. Okay, so this case about the y-axis. Yeah, or I put it here. Okay, so in this case, we should consider the method of shells, right? So same as before, we consider the slice of the uh, this one. Okay, and if we consider the particular slice here, okay, this case, now we have to approximate this volume. The volume will be delta V is approximately the distance to the rotation axis is x. So we have 2 pi x, and then multiply by the height of the region here. Of course, the height of the region here is 2 minus x squared minus x squared, right? So we'll have 2 minus x squared minus x squared, because here, so the idea is that up to this point, okay, the orange here, the height is 2 minus x squared. Of course, you have to subtract it by this small piece is x squared. Okay? So 2 minus x squared minus x squared. And then the thickness, as always, is delta x. Okay? So if you put this together, v will be 2 pi outside the integral from 0, the range of x from 0 until the intersection of this, namely x equals to 1. Of course, you can look for the intersection by considering the solving the equation. Let's say the equation is x squared equals 2 minus x squared. Of course, you have 2x squared equals to 2, x squared equals to 1. Since x is in the first quadrant, okay, since the intersection in the first quadrant, so x should be positive, so x equals to 1. Of course, y equals to 1 itself. Okay, so this is 1 comma 1. And if we go back to the integral will be integral from 0 until 1. The integrand is this one, x multiplied by 2 minus 2x squared dx. Okay. Once you get this one, okay, everything will be all right, because you just multiply this integrand and then solve the integral. In that case, we have 2 pi or 4 pi integral from 0 until 1 x minus x cubed dx. Okay, and in that case, we have 4 pi x squared over 2 minus x to the power 4 over 4 from 0 until 1. So you'll have 4 pi multiplied by half minus quarter minus 0. That will be pi. So the volume will be pi, right? Okay, any question or comment? Is it clear? Okay, so the first important step will be to sketch the graph, find the intersection point, and then slice the region, and then for each slice, approximate its volume, either the method of shells, method of dish, or washer. You use approximate delta V first. This is the important one. Once you get the approximation, then take the summation and then the limit. The volume V will be here. This is the integral. Move to this one, and then the delta x becomes dx. That's the idea. Okay. Any question? Okay. I will repeat the calculation on the whiteboard. So here, first, we have to find the intersection. So x squared equals to 2 minus x squared. So equivalent with 2x squared equals to 2. X squared equals to 1. So here x equals to 1 or x equals to minus 1. But since x is positive, we have x equals to 1. So the conclusion will be the intersection or the curve y equals to x squared intersects y equals to 2 minus x squared at x equals to 1 and y equals to 1, the point. Okay, and in this case, okay, you may consider the sketch of the curve 0, y equals to x squared, y equals to 2 minus x squared. The point here is 1. So the region will be, let's say, this one. And then use the vertical slicing. Okay. And then if you take a look at the following case, then delta V is approximately 2 pi x. F of x is 2 minus x squared minus x squared delta x. And V equals to integral from 0 until 1, 2 pi x 2 minus 2x squared dx. And that will be 4 pi from 0 until 1 x minus x cubed dx 4 pi x squared over 2 minus x to the power 4 over 4 0 1. Then you can, and then you calculate the final answer. All right. Any question or comment? Okay. The next one, we'll consider the combination of the method of this and the method of shells, and then we'll see the comparison here. Okay. Okay. So the next example will be to set up the integral. Okay. To set up an integral. So in this time we do not need to calculate the integral. Set up an integral for the volume of solid when the region R is revolved about. Okay, so there are 4 questions. The difference. Okay, I will define the region R later on. But in this case, the difference is that there are four types of the rotation axis. The first one, the x-axis. The second one, the y-axis. And then the third one, let's say the line y equals to -1 and the line x equals to 4, let's say. And here R is the region on the in the first quadrant bounded by the curve y equals to, what is the formula? 3 plus 2x minus x squared, and then the x-axis, of course, and the y-axis. Okay, so first, the first step to understand the example here, we need to sketch the region. Okay, so let us sketch the region. Okay, the region is the region in the first quadrant bounded by the x-axis, the y-axis, and the curve y equals to 3 plus 2x minus x squared. Okay, so the region here is as follows. Okay, so here is the yellow region here. Okay. Now we'll consider the volume of solid if this region first revolve around the x-axis. Okay, around the x-axis. Okay. So what is the suitable method for finding volume? What is the suitable method? Method of dish or shells? Method of this, right? Okay. So for the method of this, if we revolve this around the x-axis, then same as before, we consider the vertical slicing. Okay. Also the vertical slicing. But now the vertical slicing will be to approximate the volume of cylinder. Okay. The volume of cylinder, and then the volume of the cylinder, its thickness is delta x. Of course, okay, we have to approximate its area. Its area will be pi. Okay, and then the radius is, if this is x, then the radius is 3 plus 2x minus x squared multiplied by the thickness of the cylinder, namely delta x. Okay, so this is part A. The rotation axis is the x-axis. Okay, so do you understand how to obtain the approximation here? So just simply you have okay, you have the following cylinder. Okay, the thickness of the cylinder is delta x, and the area of the base is just simply, here is the radius, is the height of this function, namely 3 plus 2x minus x squared. So that's why pi r squared multiplied by the thickness, and r is 3 plus 2x minus x squared. So pi 3 plus 2x minus x squared multiplied by delta x. So once you get this one, then v will be just a summation, and then the limit v will be integral from 0 until this one. The intersection is at 3. Okay. So 0 until 3, pi 3 plus 2x minus x squared dx. Okay, so that's the formula for the volume. If we revolve the region about the x-axis. Yeah. Okay. So that's the first step. Any question or comment? Okay, so I will save and go back to the whiteboard. Okay. Write the solution. So in A, delta V is pi 3 plus 2x minus x square delta x. So V is integral from 0 until 3. Of course, you can put pi outside the integral. 3 plus 2x minus x square dx. And then, of course, you can calculate it. Just expand the integrand and then using the fundamental theorem of calculus. Okay. So now let us continue for part B. Okay, we'll use the same region, but now what is the difference for part B? What is the rotation axis? The rotation axis is a y-axis. Okay, so first I will move slightly little bit here. B, the rotation axis is the y-axis. So what is the suitable method for this calculation? The method of shells, right? So if we revolve this from the y-axis, then similarly we consider the vertical slicing as well. We consider the vertical slicing. And if we consider a particular one here, then the approximation will be delta V. If we consider the method of shells, then the delta V is 2 pi multiplied by the average radius is x, and then multiplied by the height. What is the height? The height is 3 plus 2x minus x squared, right? Then multiply by the thickness, delta x. Okay. And V, after taking the summation and then the limit, we have V equals to the integral from 0 until 3, 2 pi x multiplied by 3 plus 2x minus x squared dx. Okay. Any question or comment? Okay. I will put it in the whiteboard. So part B, the method of shells. Gives us delta V is approximately 2 pi x 3 plus 2x minus x squared delta x. So in this case, V goes to the integral from 0 until 3, 2 pi x 3 plus 2x 3 plus 2x minus x squared dx. Of course, you can calculate the detail here. Okay, any question? So if you compare these two methods, for example, the method of shells, the method of dish, for example, is suitable if you have a function of x and then you revolve the region around the x-axis. However, if you have a function of x, but you need to revolve the region around the y-axis, then the method of shell is more suitable. And especially the method of shells, if you cannot write x as a function of y, and then you have to revolve around the y-axis, then it's really useful. Okay. So that's the difference between these two. Okay, now let us continue part C, what is part C? What is the rotation axis? The rotation axis is the line y equals to -1. Okay, so let us take a look at the picture. Okay, so we have this one. And then I will draw y equals to -1 there. So that's the rotation axis. The region is still the same. Okay, let us consider this is the region. It's the same. Okay. Now the rotation axis is y equals to -1. So what is the suitable method? The method of washer, right? So first I will write the rotation axis first. Axis is the line y equals to -1. So if we consider the method of washer, okay, the same as before, we consider vertical slicing. Okay. Okay. So let's consider vertical slicing here. And then if we consider the method of washer, then actually we'll have okay, we'll have the delta V is the volume of the following object. Okay. Of course, the radius of the smaller circle will be, what is the radius? Is 1, right? And then the larger circle will be the distance from the line y equals to 1 until -1 until here. So in this case, okay, this one is 1, and then this one is 3 plus 2x minus x squared minus 1. So in this case, delta V, if we consider the method of washers, delta V is approximately pi multiplied by the larger radius is 3 plus 2x minus x squared minus 1 squared. Then multiplied by delta x. Okay. So once again, once you get the following approximation, then just taking the summation and then taking the limit, you will have V equals to integral from 0 until 3 pi 3 plus 2x minus x squared. Oh, sorry, I made a mistake. Oh, I forgot to add it by 1 here. Squared plus 1 minus 1 squared dx. Okay. So that will be 4 plus 2x minus x squared minus 1. Okay. Any question or comment so far? Yeah, I should add it is by 1 because if you calculate the distance from here, the pink one here is just 3 plus 2x minus x squared. And then you have to here the distance is 1. So I have to add this one by this one. Okay, you get this one. Okay, any question or comment? Is it clear? So that's why you need to calculate delta V first, because the volume of solid, there is no definite formula, because the rotation axis can be varied. Can be the x-axis, the y-axis, the y-axis equals to 3, the y-axis equals to 7, for example. So that's why we need to approximate delta V first, because delta V usually is a simple object, usually a cylinder or a cylinder with the hole inside. That's the delta V. Okay. So once you get delta V, then you just simply translate this as an integrand of the following integral. Of course, you have to consider the range of x here. But the range of x, just simply, if you take a look at what is the smallest value of x, and then what is the largest value of x. All right. Any question or comment? Okay. I will repeat in the whiteboard. So in this case, delta V is pi multiplied by 3 plus 2x minus x squared plus 1 square minus 1 square delta x. Okay, do not forget approximation. Pi 4 plus 2x minus x squared minus 1 squared delta x. So V is pi from 0 until 3 4 plus 2x minus x square minus 1 dx. Okay. Of course, you can continue the detail here. All right. Any question? Okay. Let us continue. Part D here. So what is the rotation axis? The rotation axis is the line x equals to 4. Okay. So now let us take a look at the picture. X equals to 4. Oh, x equals to. Okay, so this is the rotation axis. What is the suitable method for this problem? The method of the rotation axis is the line x equals to 4. So what is the suitable method? Is it this washer or shells? Shells, okay. Okay. So this is the rotation axis. Yeah. So we have to revolve this. So in this case, the same as before, consider vertical slicing here. Okay. Okay, if we consider this one, let us consider that here is x. So, what is delta V in this case? 2 pi multiplied by 2 pi multiplied by okay. Recall the formula for the method of shells. 2 pi multiplied by average radius. So what is average radius? Average radius is the distance from the region to the rotation axis. So if this is x, so what is this one? 4 minus x. Good. Okay. And then multiply by what is the height? The height of the slices? 3 plus 2x minus x squared. And then what is the thickness? Delta x. As always, delta x. Okay, so this is the important one. Okay, this is not always x. That will be the radius. Average radius is the distance from the region to the rotation axis. Please be careful. So that's why the important one is always approximate delta V. Because if you just use the formula, then you just replace this by x, and the result will be the different object. Actually, if you replace this by x, that will be the volume of solids obtained if you revolve the region to the y-axis. But if the rotation axis is the line x equals to 4, then the distance is 4 minus x. That's why you have 4 minus. Okay. All right. So after take the summation and then take the limit, you have the volume as the integral as integral from 0. What is the this one is 3, right? The 3 2 pi 4 minus x multiplied by 3 plus 2x minus x squared dx. Okay, so that's the key formula here. All right, of course you can expand the integrand and then calculate the integral. All right, any question or comment? Okay. So the rotation axis is the line x equals to 4. So the approximate for delta V is, okay, in this case, you have 2 pi multiplied by the average radius is 4 minus x. The height is 3 plus 2x minus x squared, and then multiplied by delta x. Okay, take the summation and then the limit, you have V equals to from 0 until 3, 2 pi 4 minus x 3 plus 2x minus x squared dx. Then expand this, you'll have the result. Okay, any question or comment? So it's important if you apply the method of dish, method of washer or cells. The first important thing is to approximate delta V. That's the most important step. Once you have the correct approximation, then you are almost done. Write the integral. Be careful with the lower limit and upper limit of the integral. Then you get the result once you calculate the integral. Okay. All right. Good. Okay. All right. So now let us continue. So the next material will be on about the application of integral in physics, especially if you consider, let's say, the okay, about the work here. Oops. Yeah. Okay, so the basic formula for the work is that work equals to force multiplied by the displacement. Okay. Okay. Of course, okay, if the force is constant, then you simply multiply the value of the force is a constant. The displacement will be the difference between the initial and the end point of the object. Okay. Okay. Now, let us consider the following problem. Suppose that we want to move the object from x equals to a until x equals to b here. And now the force is not a constant. It depends on x here, f of x. Of course, the idea is that if we consider a partition of the interval a comma b into a smaller subintervals. Okay, let's say x0 equals to a, xn equals to b, and in between we have x1, x2, x3, x4. In general, xi minus 1 until xi, and xn minus 1 until xn here. The idea is that if the interval, let's say if we consider the subinterval xi minus 1 until xi minus 1 until xi, and if the interval is small here, I mean, if the function is continuous, f of x is continuous, then you'll see that the value of x, the value of f at xi minus 1 and the value of f at xi is not that different. Then we may assume that the value at this point, at this interval, is a constant. Okay, consider this and assume that f of x, let's say, equals to fxi on this interval. Assume this one. Okay, then the work done in moving the particle from xi minus 1 to xi is, let's say, delta w is approximately fxi multiplied by xi minus xi minus 1. Okay, so you'll see that this is the force, and then this is the displacement. Okay, and the total work will be then w is approximately just the summation I equals to 1 until n fxi xi minus xi minus 1. Of course, remember that this is the Riemann sum. Okay, of course, if you take the limit as the norm of the partition, or delta x tends to 0, okay, of course you can write this as summation I equals to 1 until n fxi delta x. Yeah. Then if you take delta x tends to 0, you'll have then the work done in moving the particle from x equals to a to x equals to b is w. It's just a simply limit as delta x tends to 0 of the Riemann sum I equals to 1 until n fxi delta xi. And of course, if the limit exists, then the value will be integral from a until b fx dx. Okay, so that's the formulation of the work done in moving the particle from x to a until x. So this is the general formulation here. Okay. Now, let us consider the application or in this example of this concept in the problem of the spring. Okay, application to springs. Application to springs. Okay. So in this case, let us consider. Probably you have learned this in physics. If you consider a springs, okay, let's say this one, and okay, assume that this is the natural length of the spring. Okay, from this one until this one is the so-called the natural length of the spring, and then we'll write this as a 0, and then here 1, 2, 3, 4, and so forth. Okay, and then we have to pull the string to the right, so the string will be stretched. Okay, let's see. Oops, I will try to do my best to. Okay, probably I will slightly tilt it this. Okay. Okay, so assume that in this point we'll have 0, 1, this is x, this is 2, 3, and 4. Okay, so we pull the strings, so it's stretched. Then the force, okay, the formula for the force will be f of x by the Hooke law. F of x equals to k of x. Here, k is the spring constant. Okay. That's the formula. Okay. Of course, the value of k here depends on the material in making the string here. Okay, so that's the formulation. Now let us consider an example to this problem where yeah, we will consider the example of string problem here to calculate the work here. Okay, so the example is as follows. Suppose that let or suppose that the natural length of a spring is, let's say, 20 centimeter. Yeah. Okay. Let's say 20 centimeter. And then if it takes, let's say, the force to move the spring, let's say 12 Newton, to keep it extended, let's say 4 centimeter. Okay, then the question is then find the work done in stretching the spring from its natural length, namely 20 centimeter, to let's say a length of, let's say 30 centimeter. Let's say this is the problem. Okay. Okay. For example, in this case, the situation is the natural length is 20 centimeter. Okay. And then you have to extend the spring. You have to stretch it until its length is 30 centimeter. Now the question is, what is the work done in moving the spring from 20 centimeter until 30 centimeter? Okay. Okay. Now let us consider the following solution. Okay. Of course, to make it compatible, you have to convert the unit here into suitable formula, because the force is measured in Newton. Then we have to convert the length of the spring or the displacement here in meter. So in this case, first, of course, you have to rewrite the natural length of the spring. Is here is 0.2 meter. Okay, so you have to first convert the unit into a suitable unit, right? And then the next step will be to find the spring constant, to find K here. How do we find K? Here we have the force is 12 Newton, and then the displacement here is 4 centimeter. Okay, so since F, okay, so of course, first let us write the formula. Not that F of x equals to K of x. Okay, and then since F of, okay, 4 centimeter is 0.04 meter. Okay, so if x equals to 0.04, what is the force? 12, right? We have K equals to 12 divided by 0.04. That will be 300, right? So K is 300. Therefore, F of x equals to 300x. Now, okay, so we just obtained the spring constant and then the formula for the force. F of x equals to 300x. The next step will be to insert this formula to this formula of the work. Okay, so the next step will be, so the work done in stretching the spring from 20 centimeter or 0.2 meter to 0.3 meter is, okay, W equals to integral of f of x dx. That will be the integral of 300x dx. Okay, so here is the key point. So the integral will be, you'll see that from the natural line, so the starting point will be x equals to 0. Okay, so from here to here, we have to move 0.1 meter, right? So the lower bound is, the upper bound is 0. So from 0 until 0.1, 300x dx. That's why if we calculate the integral will be 150x squared 0.1. That will be 150 multiplied by 0.1 square minus 0 square. That will be 1.5. Okay. So the work done in stretching the spring from its natural length, namely 0.2 meter to 0.3 meter, is the integral from 0 until 0.1 fx dx, and then the formula of fx is 300x. So antiderivative of 300x is 150x squared. Then put x equals to 0.1 and 0. Get 1.5. Okay. I think yeah. Any question or comment? Okay, any question or comment so far?